So last we talked about describing scatter plots. Are you kidding me? We talked about describing scatter plots. We talked about direction, whether it was positive or negative, the form, right, whether it was linear or curved or had no form, and the strength. And strength was very subjective, right? It was really close to a perfect line, so it was strong. It was real scattered, so it was weak. It was kind of in the middle. It was moderate. Now we're going to talk about correlation, which is a numerical measurement, a numerical calculation of the strength of the relationship. Correlation, we use the letter R. So I'm going to let you, to quantify the strength of a linear relationship between two quantitative variables, we use the correlation R. I'm going to have a definition here for you. Okay, you can write this down. Correlation, variable R, is a measure of the strength and direction of a linear relationship between two quantitative variables. Important note here that it is for quantitative variables only. You can compare the association, which we did in the first part of this chapter, of categorical and quantitative variables, but you can only use correlation with two quantitative variables. Correlation has some really important properties. Correlation R is a value between -1 and +1. If the relationship is negative, then the correlation is less than 0. So if it's a negative correlation, it'll be a negative slope. If it's a positive correlation, if it's a positive relationship, it's a positive slope. If R is 1 or -1, then there is a perfect linear relationship. All the points are exactly on a line. And if there's very little scatter from the linear form, then R is close to -1 or +1, right? So if it's not perfect line, but it's scattered a little bit, it's really close to 1 or -1. The more scattered it out it is, the closer R is to 0. Okay, so we're going to look at these scatter plots. You don't need to draw this in your notes, but here are 6 scatter plots and the corresponding correlation. So the first scatter plot here is an example of what a correlation of 0 would be. It just looks like a big cloud of points, right? You can't really tell any direction. It has no form, and it's really scattered. As we get to a -0.3 correlation, you can see that there is an overall negative pattern, right? But the points are still pretty scattered. As you get to a +0.5, like you see a positive pattern. They're a little bit less spread out than the 0.3. Even more less spread out if you go to a -0.7. A 0.9 is even closer together, and then a 0.99 almost looks like this perfect line, right? They're not a perfect line, but they're really close together. Okay. So there's some examples of what correlation and the corresponding scatter plot would look like. Okay, so go back to our thinking about our candy grab example. This isn't our data. This is the data from Mr. Tyson's statistics class. There are 23 points because 2 students had hand spans of 19 and grabbed 28 Starburst candies. They were assumed to be outliers. Okay. I think Marlene was our outlier with her fingernails, right? Would you expect this correlation to be positive or negative, right? Is R greater than 0? Or is it less than 0? Is it closer to 0 or closer to positive or -1? What do you think?
It's closer to 1.
Right, it's closer to 1 and it's positive.
Yeah.
So R is greater than 0. Okay. It's positive because it's increasing, right? No, I don't think you need to write this, because then you'd have to draw the graph for anything to make sense. right? Yeah. So it's closer to 1. It's positive, which means r is greater than 1. Why? Because it's an increasing graph. The points are in a nice, like, linear pattern. Like, you can see a linear pattern that's pretty strong, so it's going to be closer to 1 than it is to 0. 0 would be more of a cloud of points. Here is another scatter plot. To see if seat location affects test scores, a statistics teacher randomly assigned students to seat location in his classroom for a particular chapter and recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment is which row the student was assigned, where row 1 is the closest to the front and row 7 is the farthest away. Here's a scatter plot showing the relationship between the row and test score. Is the relationship positive or negative? Yeah, I kind of see a little bit negative, right? Right? It has a little negative pattern. So that means r is less than 0. And then would you say it's closer to 0 or closer to negative 1? It's closer to 0. Okay, closer to 0 because it's pretty spread out, right? Okay, so the scatter plot shows the relationship between the 40-yard dash times and the long jump distances for a small class of 12 students. The correlation is negative 0.838. Interpret this value. So when we're interpreting, we say positive or negative. It's negative. And we said 0.83, is it strong, very strong, weak, or moderate? That's very strong or strong. Okay, it's kind of a judgment call. Okay, let's say if the absolute value of r is between 0, from 0 to 0.3, we're going to say weak. If it's greater than 0.3 to 0.6, we're going to say moderate. Let's say 0.6 to 0.85, we're going to call strong. And 0.85 to 1, we'll call very strong. Okay. So we'll make our own little scale that we're going to use when it becomes like a judgment call. And remember, that's the absolute value of the number because the negative sign tells you the direction. It doesn't have anything to do with the strength. Okay, a correlation that is close to 1 or negative 1 does not imply that an association is linear. Write that into your notes, please. Just because the correlation is close to 1 or negative 1 does not necessarily mean it's linear. This scatter plot shown here shows the weight of diamonds in carats and the price. It has a correlation of 0.93, but it's clearly curved. So correlation alone does not provide information about form, which is why it's always important to look at the scatter plot. So we have to look at the picture and the numbers, not just the numbers. Now, while correlation is a good way to measure the strength and direction of a linear relationship, it has limitations. Most importantly, correlation does not imply causation. So if you haven't written that in your notes already, do so. Correlation does not imply causation. In many cases, two variables might have a strong correlation, but changes in one variable won't necessarily cause the changes in the other. Here's a weird scatter plot showing the relationship between the total revenue generated by skiing facilities in the United States and the number of people who died by becoming tangled in their bed sheets in 10 recent years. Yeah. The correlation for this data is 0.97. Does that strong correlation between these two variables suggest that an increase in skiing revenue causes people to die by becoming tangled in their bed sheets? No. No, that would be totally silly. Don't go skiing. You might get tangled in your bed sheets. Right? So just here's an example of two totally random things put onto a graph together, has a strong correlation, but that definitely does not tell us that one thing causes the other.